All right. So we're into chapter 2. Oh, hold on one second. I'm going to pause my recording. All right. So types of hydrocarbons. There's 3 types. We're going to look at all of them. And actually, this is chapter 2. This is chapter 3. And this is chapter 4. Chapter 5, hands down my favorite chapter. We'll take all of this and kind of apply it to hydrocarbon chemistry, or maybe what I should say is the oil and gas industry. So let's look at the definitions of 3 of these. I think I've already done these slides, haven't I? Did we do these last day?
Yes.
Yeah, we did. I remember looking at this one. Yeah. Okay. Cool. Alkanes. Okay, I don't think we did this because I would remember that. So let me just go back here. Chapter 2, we are dealing with saturated hydrocarbons. Okay, so we're going to kind of forget about unsaturated and aromatic for right now. We'll come back to these 2 in chapters 3 and 4. Really what we're going to look at in chapter 2 is alkanes or cycloalkanes. And I mean, the word kind of explains itself, cyclo as in a ring. Okay, acyclic means no ring. Okay, remember I was talking about that word the other day. If you say like atypical, it means it's not typical. Acyclic, not cyclic. All right, all of the bonds in all of these are single. Now, there are formulas on this page that you guys definitely do not need to memorize. Okay, but I'm not saying they're not good to know, but you don't really have to memorize these. Again, nothing in this course is really about the molecular formula. We will be using skeletal diagrams and we will be naming. This is the molecular formula, not really part of this course, maybe more part of 1121. So you do not need to know the formulas, but the reason that this formula is so complicated looking is because when you have a ring, you actually have less hydrogens because, so let's look at on the left. 3 hydrogens here, 2 hydrogens here. I guess I shouldn't draw it like that. 2 hydrogens, 2 hydrogens, and then 3. Okay? But the minute you have a ring and you close it up, well, then you don't have this thing on the end that has 3 hydrogens anymore. So we have 2, 2, 2, 2, and 2. You do not need to know these formulas, okay? So don't worry, but it is interesting to know. One thing I'll mention too is don't forget that magic number of 4. Every carbon has 4 bonds. It could be to a couple hydrogens. It could be like a double bond with another carbon and then 2 hydrogens. But every carbon, and this is a mistake I'll never forget. In my first organic chemistry course in university, I remember I did a test or an assignment and I forgot to put 3 bonds on something. And my professor was really mean, and he just kind of made fun of me for it. I'm like, you guys know when you do a test, you make a silly mistake all the time. I've made so many, and he said, your second year chemistry major, and you forgot to put 4 things on the carbon. And I was like, man, I'm sorry. It was a long test. So ever since then, I never forget that magic number 4. Every carbon has 4 lines coming from it. Okay, there are exceptions like radicals and things like that, but that's not for us. So you guys, if there's one thing you really need to memorize, it's this table. And I'm going to go easy on you. You only need to know the first 10. We're not going to go past 10 carbons. A lot of the products especially the where you make your money when you fractionally distill petroleum. A lot of them are the smaller hydrocarbons. LNG, um, things like used for polymers. These are typically what you see coming out of the distillation fraction at the very end or top of it. And we'll talk more about that in chapter 5. So I'm going to keep it to the first 10, and there's really nothing to explain here. These are just 10 words you have to memorize. Some of the words are quite easy and logical, as in pentane or hexane, a pentagon or a hexagon. These are shapes in mathematics. An octagon, right? It's an 8-sided shape, like an octopus has 8 tentacles. Oct means 8. So, there's a few that really stand out that make a lot of sense, but the rest you have to memorize. So, methane, ethane, propane, butane, pentane, hexane, heptane, octane, nonane, and decane. You must know. Now, what about the other side of the slide? What does that mean? Well, this we'll get into a little later, but this is when they are branches. Oops, I forgot an H there, on your carbon chain. So like if I had a long carbon chain, this would be a methyl group. Okay, let me pick a different color. And we will come back to this, don't worry. So if this doesn't make any sense right now, don't worry. This is kind of what we're going to do today. So these are groups or branches on a long carbon chain. And honestly, between us, if you know these first 4, you'll probably get by with most things in this course. The problem with really long branches is the rule, and we'll talk about the rule maybe today, maybe tomorrow, but the rule in chemistry is you name the alkane based on the longest chain. So when your branch, and they call it an alkyl substitute, but when your branch gets to be really, really long, then typically that's not a branch, it's part of the carbon chain. And you'll see me do this. Let me see. Yeah, we might get into naming today. We might get into a little bit of naming. So you'll see this maybe today. If not, you will definitely see it on, when's our next class? Monday's class. All right. Let me see who's here, by the way. 12 of you, almost everybody. Since I have 12 of you, just remember that your lab schedule is online, and you do, let me just double check, but I'm pretty sure you have a lab next week. 99% sure. This is all in your course information sheet on D2L. So yes, September 20th to 24th, so next week, on Tuesday morning, you do have a lab. You actually have a lab the week after that as well, and then we'll take a little break. So there is a lab next week. All right, section 2.2. This is the very quick. The funny thing about this is we won't look at this stuff until maybe the third lab. I almost said chapter 3, I mean the third lab. Your third lab, we will look at the boiling points of alkanes. It's a pretty cool lab, but this is good to know for your test. And remember, you'll have your test in week 7 in October. So it's not until October. Okay, alkane molecules. So physical properties of alkanes. Physical properties are different than chemical properties. So like a chemical property would be like the reactivity of the molecule, so when I say like alkali metals react with water, that's a chemical property. But if I said alkali metals are shiny, solid, and silver, All of those properties are physical. So alkanes, these are, some are solid, some are liquid, some are gases. It depends on the temperature. So this gets a little interesting. But one thing that's a very interesting property is that they are non-polar, meaning if you can remember chemistry 1120 and your intermolecular forces, I know that was a long time ago for some of you, but polar things and non-polar things do not mix. So if I mix together oil and water, the oil will float on top of the water. The oil is non-polar. Now, when I say oil, I mean that really is, that it could be a lot of things. My typical example of this is one you could do if you're home right now. You could go into your kitchen and get a glass and keep it away from your dog, but get a glass and put some water in that glass and then take some cooking oil. So olive oil, canola oil, vegetable oil, ghee, anything like that. Whatever you guys use for oil, and put that in. And you'll notice if you wait a few minutes, um, they'll separate. The oil will float to the top. And this is a good and bad property. It's good in the sense like when you look at oil spills. So something happens in the ocean, an accident occurs and there's an oil spill in the ocean. The oil will not mix with the water, not really, and it will float to the top, which makes it a little easier to separate. And I'll move on from this, but like there's so much I could say about this property. But one thing that you'll find interesting is in the oil and gas industry, when you pump the oil or remove it from the ground and you're pumping that oil through pipelines or pipes, a lot of times it's mixed with water. It could be ocean water or water that the company is putting in. When you take alkanes and you put them in a pipeline, so it could be coming from your distillation or just even coming from the ground, with the pressure and the turbidity is not the right word, turbulence is what I'm trying to say. The pressure and the motion of the water, you can actually see them mix. And again, you could do this in your kitchen. If you have a jar or a big glass, and you mix oil and water, and you stir it enough, like go crazy, you could put it in a water bottle and shake it like crazy. It will mix a little bit, but then eventually it will separate. So we'll talk more about this in chapter 5. It's really interesting stuff, and we'll talk about like mixing and separating. When oil and water mix, it's called an emulsion, and it's not something that you want. You typically do not want emulsions. Ooh, shampoo and water. Well, that is actually, and I won't get into this too much, but that is actually an outcome in this course. And I just remembered about it in chapter 5. Soap, and I know you're like, soap and shampoo are same but different, obviously. Shampoo, it's usually pH balanced for your hair, but the key, what makes soap and shampoo the same is that, and it's so simple how it works, it creates bubbles and a slippery surface for the dirt to wash off. Now, I'm not talking about antibacterial soap, that has chemicals in it that kill bacteria. Normal shampoo, normal soap, the way that they work, it's so deceptively simple. They are so slippery that the dirt on your hands, the germs, the bacteria, the dirt in your hair literally slip off when you wash it with water. But it gets even more complicated because soap is an emulsifier. Soap helps oil and water mix. So when your hair is greasy, when your hands are greasy, and you use soap or shampoo, the soap helps the shampoo, or sorry, helps the grease or oil or dirt in your hair mix with the water. So when you wash it, it all goes down the drain. So I could talk more about this, but shampoo, if you again went to your kitchen and you took a little bit of soap and mixed it with oil and water and then mixed it all together, the shampoo or soap would actually help them mix and create an emulsion. Really interesting. And Naim, that is actually an outcome, and we'll talk about that in chapter 5. There is an outcome in your course that says, explain why soap is a good emulsifier. So we'll talk more about that in chapter 5. Okay, sorry, I'm rambling, but it is truly because I find this stuff so interesting. So I'll go a little quicker now and you guys can get out of here. I know you probably have more classes today, but you know, we're doing okay for time. So let me do a couple more physical properties. I definitely want to talk about boiling points, and then maybe I'll just introduce the next part and that's it. So a couple more minutes. So all alkanes, now again, there's thousands and millions of alkanes, I'm sure, different branches, different sizes, different lengths, but typically alkanes are less dense than water, which means that's why they float on water. And again, I'm not saying olive oil or cooking oil are necessarily straightforward alkanes, but they are non-polar, so they won't mix. So if you consider the two properties of alkanes, they are non-polar and they are less dense than water. That means when you mix them with water, they will float on top. And you'll see this in lab 3. I don't think we'll talk about this in lab 2, but lab 3, you'll see this. This is something you definitely need to know. This is honestly a fundamental property of the separation of petroleum products. The whole science behind, well, okay, no, but not the whole science. The major scientific property that allows us to take petroleum from the ground, crude oil, and separate it into usable components is the boiling point. You guys probably learned this in another course. I think it was 2430. I taught that many, many years ago. But the idea is if you start to heat up crude oil and you start to get it to boil, it will separate based on its boiling points. It's fractions, they call it. And we're going to do that in a lab. I have a little fractional distillation column we'll use in the lab. It's really fun. So alkanes, they increase the boiling point or melting point. It increases the bigger the molecule is. So the larger the molecule, the more energy it's going to take to boil it, to change it into the gaseous phase. So methane, very tiny molecule, has a really low boiling point, meaning it's a gas at room temperature. But then when you get into like pentane and hexane and octane, they start to become liquids. Then when you get even bigger, like you're looking at 20 carbons or 40 carbons, they would be solids. Like paraffins or waxes is kind of what you could imagine there. This, guys, if you could see my face, and I'm not opposed to turning my camera on, but I'm winking right now. If you could see my face, this wink moment here is, this is typically a question I ask just to see who's been reading their notes. If I give you an alkane and the corresponding, and I'll explain what that means in a second, corresponding straight chain alkane, cycloalkanes will have about a 20 degrees Celsius higher boiling point. So what do I mean? Well, let's take pentane. So 2, 3, 4, 5. That's pentane, 5 carbons. That's not the formula. C5H12 would be the formula, but I don't care about the hydrogens, just the carbons. If I take cyclopentane, okay, looks like a little house. This is still C5. It's cyclopentane. And I asked you, wink, 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 so I'm winking right now, which of these chemicals have the higher boiling point? And again, which do you think? That's the key word here. We're just using chemical properties to try and predict. Real life can be different, especially when you start adding like bonds and functional groups. But you know, if we had to use our chemical properties to predict, this would have the higher boiling point by about 20 degrees Celsius. And it's just because of the structure of the ring. It takes a little more energy to turn that into a gas. Remember, temperature is just energy, kinetic energy. So it just takes a little more energy for those molecules to change phase. All right, I think I have one more slide, and I'll finish it up there. I'll just maybe introduce the next section. The next section is the most important section of the month of September. So tomorrow, well, next class on Monday, we have a nice class late that day, but you definitely want to come to class Monday. Okay, so the finale of today, this we will look at a little later in lab 3. So that's not next week, but the week after. Lab 2 is next week. But yeah, we're going to look at the melting point or boiling point of these. And honestly, I'm going to focus in this course on the boiling point. The boiling point is what we use to separate these chemicals in what's called a distillation tube, or you know, in industry you would use like a fractional distillation column. You definitely do not have to memorize these numbers. What you should notice with these numbers is the trend. And the trend, and if you're not familiar with that word, like pattern, is as my carbons get bigger, my boiling point gets higher. And it might be a little confusing to see a number like negative 164, negative 89. All that this means is those are all gases. And where it really gets interesting, sorry, and I should say gases on Earth. There's not many places on Earth, there are, but not many places that get colder than minus 42. But it gets really interesting here, because in this range, you're approaching Earth temperatures where, I mean, in Doha right now, my phone says it's 38. So in Doha, in Qatar, in the Middle East, today outside, pentane would be a gas. It would be boiling because it's again, if my phone is correct, it would boil at 36. So it will be a gas. But in Canada, where I'm from, now Canada's really big, so let me type in my hometown. See what the weather's like where my parents are. Oh, I guess I'm gonna need weather. It is 15 degrees Celsius, so pentane would not be boiling, it would be a liquid. So you don't have to memorize any of this, but just know that some of these butane and pentane, they can be a liquid or a gas in nature, in real life. And I think in the lab, we have some pentane and hexane, and we're going to look at these two because we can easily heat them up and turn them into a gas. I will give you a warning, and maybe I should hit stop record, but I won't. I'll leave it on for honesty. We've spent a lot of time, a lot of research, a lot of practice to get these labs to work. And now when I say these labs, I mean the distillation labs. And I have to be honest, there is just one critical problem in Doha. the tap water in the lab is too warm. So we have a problem with the condensing part. And you'll see all this in the lab, maybe not next week, but the week after. So if you have 7 labs, I can guarantee you 5 of them are perfect. 2 of them where we actually distill, we've had some issues. We just need cold water, and we can't get cold water at the college. It's especially when we do the labs, or they're typically done in like October, so it's still pretty warm outside. Anyways, that's okay. Sometimes it works. We just gotta be careful. So guys, I'm done. I just reminder that tomorrow, I say tomorrow's the weekend. Enjoy your weekend. But next class, so Monday afternoon, be here for this. This is huge. Nomenclature means naming. And this is a fundamental topic that you'll need in chapter 3 and 4. So definitely come to class on Monday, and then I'll see you in the lab on Tuesday. So that's it. I'm going to hit stop record.